Good morning. Today we're going to look at section 7.5a on exponential and logarithmic equations. And our goal today is to solve exponential equations. So any equation that contains the form b to some power, where there is a variable in the power, such as a equals b to the cx, the exponent includes the variable, that makes it an exponential equation. So we're going to look at two different strategies today. The first one is when the numbers of both sides of the exponential equation can be written with a common base, we're going to rewrite it and set the exponents equal. Remember to isolate the exponential term first. So if we look at our power chart, we notice that 16 is the same as 2 to the 4th power. And by putting that using a base of 2, we now have a common base. Both sides have a 2 being raised to a power. Since 2 to a power has to equal 2 to the same power, then the 3x plus 1 power has to equal the other side's power, which is a 4. Then we simply solve that linear equation. Subtract a 1 to the other side and divide out our 3. All right, for the second one here, now 16 cannot be written as a power of 8. However, they both could be converted into powers of 2. So 16 is 2 to the 4th power. It is still being raised to a 3x power. On the other side, 8 is the same as 2 to the 3rd power. So again, we're using a 2 for our common base. Then we set our powers equal. Notice on the left side we have a power raised to another power, and our exponent rule says we multiply those. So we get 12x on this side has to equal 3 on this side. And then if we divide out the 12, x would have to be 1/4. For the third example, we have a 5 to a power on the left side, and we can write 125 using a 5. All right, looking at your power chart, 125 is the same as 5 cubed. So we have 5 to the x plus 1 equals 1 over 5 cubed. Now we still have to move that 5 up to the numerator. And when we flip a fraction over, our power ends up changing to a negative. So 5 to the x plus 1 would have to equal 5 to the negative 3 power. That's what's going to cause it to flip over. Now we have a common base, so we set our powers equal. So x plus 1 has to equal negative 3. If we subtract 1, x would have to be negative 4. All right, looking at our next example. Notice there's a 3 on the outside of the parentheses. It is not being raised to the power. So we want to isolate the exponential part first by simply dividing the 3 to the other side. So we have 7 to the 2x now equals 147 divided by 3, which is 49. And now we work towards getting that common base. We can think of 49 as 7 squared. So now we have 7 to the 2x equaling 7 squared. That means 2x would have to equal 2, or x would have to be a 1. All right, for the next one, to get our exponential part by itself, our first step would be to subtract our 3 to the other side. That still leaves me a negative in front of that exponential piece. And so we want to divide that over to the other side. So we have 4 to the x equals 64. And if you look at your power chart, 64 is the same as 4 cubed. So x would have to be a 3. All right. For our next example, we have a 3 to a power on the left. We have 27 to a power on the right side. We can convert the 27 into 3 cubed. But be careful because that 27 is being raised to a power, so our 3 cubed is still being raised to that power. All right, on the right side, we have a power to another power, so we multiply those. This would be 3 to the, if we distribute, 3x plus 3. And now we have a common base, so we can set our exponents equal to each other. So 4x minus 3 would have to balance with 3x plus 3. Subtracting 3x's over to the other side leaves me 1x. and then adding the 3 to the other side leaves me with x being a 6. All right. Our second strategy that we're going to look at is when the numbers cannot be written in a common base. So for example, we've had problems, we had a 3 here and a 27 on the other side. We could get a common base. But what happens if that 27 instead was a 26? Then we can't get a common base for those. So we have another option. The first thing we want to do is isolate the exponential term, just like before. But now we're going to use log base b on both sides. So we're going to take the log of each side, but we're going to use the base that we have in our exponential equation. So for our first one here, our base is a 15. 15 is being raised to a power. So we are going to take log base 15 of each side. So log base 15 of 15 to the 3x has to equal log base 15 of 285. Using our properties of logs, we know that log base 15 of 15 to a power is just the power. So once you get these pieces here to match, this part drops out, and all we have is our 3x. Then we can use our change of base formula from yesterday to convert the right side. So 3x would equal the log base 10 of 285, so we can use that common log key on our calculator, divided by the log base 10 of 15. All right, so we're going to grab our calculators and figure out what is the log of 285 divided by the log of 15. Remember that there are going to be parentheses that you're given, and you have to close that off before you move to the bottom denominator piece. So we want the common log of 15 common log of 285. Close off our parentheses, divided by common log of 15. All right, so we get this decimal 2.08729, etc. And then our last step would be to divide out the 3. So let's take our decimal here and just divide by 3. And we end up with an answer of 0.695763, etc. Typically, logs are given out to 4 decimals. So let's take this to 0.6958 if we round it. Okay, looking at our next one. We have 2 to the x plus 5 equaling 100. We are going to use our base of 2. So log base 2 of 2 to the x plus 5 has to be equivalent to log base 2 of 100. We're taking the log of both sides. On the left, log base 2 of 2 to a power is just the power. On the right, we use our change of base formula. So the log of 100 divided by the log of 2. And then to complete this, we're going to subtract the 5 to the other side. So we're going to grab our calculators and figure out what this is. And then we're going to subtract 5 from it. So the log of 100 divided by the log of 2. Common log of 100. There we go. Common log of 100 divided by the common log of 2. And then we had to subtract 5 from that. So we end up with 1.6439 if we round that. All right. For the next one, we have to subtract the 1 first because we want to isolate that exponential piece. So we're going to subtract 1, so 3 to the 2x now equals 189. Our base in this question is a 3, so we're going to use log base 3 of 3 to a power and log base 3 of the other side. Okay, on the left, log base 3 of 3 to a power is just the power. These drop out. On the right, we use our change of base. So log of 189 divided by the log of 3. Once we get that in our calculator, then we are going to divide it by 2. All right, so again, let's grab our calculators. We want the log of 189 divided by log of 3. And then we're going to divide that answer by 2. All right, so final answer is 2.3856. All right, our next one, we have a 2 that's in front of our exponential piece. It is not being raised to the power. So we're going to go ahead and divide both sides by 2 first. So 4 to the 2x plus 1 has to equal 87 divided by 2, or 43.5. Then we can take the log of both sides. We're going to use our common base of 4. So log base 4 of 4 to a power equals log base 4 of our other side. Our log base 4 of 4's drop out. We get 2x plus 1. On the other side, we use our change of base. All right, so let's go ahead and get a decimal. Log of 43.5 divided by log of 4. All right, so we have 2.72147, and then that is equal to 2x plus 1. And then to solve this, we're going to have to subtract 1. So 2x equals 1.72147, and then we're going to divide that by 2. All right, so we're going to subtract our 1, and then we're going to divide it by 2. So we end up with 0.8607. All right, remember that common log, that is that base 10. It's super convenient because our calculator already operates in base 10, so we don't have to overcomplicate something like this. Our base here is a 10, however, we need to get rid of that 3.5 first. So we now have 10 to the x plus 4 equals 140 divided by 3.5, ends up being just 40. Now we can take the log of both sides, but we're going to use log base 10, which is the key that we have on our calculator. Log base 10 of 10 to the x plus 4, and log base 10 of 40. So x plus 4 equals the common log of 40, and then we'll simply have to subtract 4 from that once we get our answer to the log of 40. All right, so common log of 40, we're already in base 10. And then we wanted to subtract 4 from that. So our final answer would be negative 2.3979. All right, our last question today. It says, wood is a sustainable, renewable natural resource when we manage the forests properly. Your lumber company has 1,200,000 trees. You plan to harvest 7% of the trees each year. How many trees will it take to harvest? How many years will it take to harvest half of the trees? All right, so we start out with 1,200,000, and we are harvesting 7%. That means we're taking away 7% of the trees. So 1 minus 0.07, it's an exponential decay problem. We're looking for how many years it takes, so what time, until we've harvested half of them. Well, if we had 1,200,000, then half of that would be 600,000. So that's what we want to have left when we finish. Our first step would be to divide out this 1,200,000. And that's going to give us a 1/2 on this left side. On the other side, 1 minus 0.07 is 0.93. And now we can do the same thing we've been doing. Our base in this case is a decimal, 0.93, but we can do that. We can take log base 0.93 of 0.5 equals log base 0.93 of 0.93 to the t power. On the right-hand side now, these drop out. We just get our t for time. On the left side, we use our change of base. So we're going to take common log of 0.5 divided by common log of 0.93. All right, so common log of 0.5 divided by common log of 0.93. So it's going to take just a little over 9.5 years for us to harvest half of the trees. All right, let me know if you have any questions on solving exponential equations.